So imagine for a second that the entire universe is just this giant, inescapable blender. Basically, anything that goes in gets completely mixed up, destroyed, and thermalized until literally all of its original information is just lost to the chaos. In physics, this is widely considered the ultimate unbreakable rule of isolated quantum systems. But what if I told you that gravity itself might have a secret escape hatch to avoid this cosmic blender? Well, welcome to today's Explainer, where we're going to unravel a seriously fascinating paper titled Quantum Scars from Holographic Boson Stars. We're basically going on a detective journey today to figure out how certain self-gravitating systems seemingly break the completely unbreakable laws of thermalization. Here's the roadmap for our investigation today. First, the rule of chaos. Second, enter the quantum scar. Third, the holographic boson star. Fourth, 3 pieces of evidence. And finally, bridging chaos and gravity.
All right, part 1, the rule of chaos, or what we can call the universe's ultimate blender. To really get into this mystery, we first have to establish the fundamental scientific wall we're up against, the inescapable law of quantum chaos. It's formally known as the eigenstate thermalization hypothesis, or EHTH for short. In the realm of quantum many-body systems, EFS basically dictates that isolated systems are going to inevitably thermalize. They act exactly like that chaotic blender. I mean, think about it. If you drop a strawberry and a banana into a blender, after a few minutes, you just have a uniform smoothie, right? The original, distinct information of the fruit is totally destroyed. And in the holographic universe, black holes are the absolute poster children for this. They are paradigmatic, maximally chaotic thermal states. They obey EFH perfectly. Whatever falls in is scrambled into pure thermal chaos. That's the rule, period.
Let's move to part 2. Enter the quantum scar, the rule breaker.
Because every good mystery needs a rebel that completely defies the rules, right? Meet the quantum many-body scar. This is a highly atypical, non-thermal state that is embedded deep within an otherwise completely chaotic spectrum. Going back to our blender analogy for a second, imagine you turn on the blender, but miraculously, right in the middle of that swirling, chaotic smoothie, there's this tiny perfect pocket where the strawberry and banana somehow unmix themselves and just bounce back and forth in their original forms. It's wild, it's a total evasion of conventional ergodicity. Originally, these scars were discovered in very specific, constrained quantum systems, like Rydberg atom arrays. They essentially represent these hidden integrable structures where information simply refuses to die.
And that brings us to the central question of the source material we're investigating today. We already know scars can exist in constrained, microscopic quantum systems on a lattice, but can these rare, non-chaotic scars actually exist in the ultimate chaotic environment? Can they admit to gravitational or holographic realization? Put simply, can a massively complex, self-gravitating system actually harbor these miraculous pockets of order? Which brings us to part 3, the holographic boson star, our prime suspect. To answer that big question, we need to introduce our outlier. Let's line up our suspect right next to the usual culprit to see the contrast. On one side, we've got black holes. They represent maximal chaos, total thermalization, and they have that infamous one-way event horizon. Literally, nothing escapes. But on the other side, we have our prime suspect, asymptotically anti-de-Sitter Mini-Boson stars. These are compact, self-gravitating Bose-Einstein condensates. And the absolute most important thing about them? They are horizonless. Because they don't have an event horizon, they carry zero thermal entropy. They don't just absorb particles like a black hole does. They can actually reflect them through boundary conditions, which, you guessed it, makes them the absolute perfect candidate to harbor these non-thermal scarred states. Now, the physics here is super interesting because we can actually chart the physical limits of our suspect. The data maps out a one-parameter family of regular boson star solutions. If you look at the frequency and the mass, plotted against the central scalar amplitude, you can see how the star interpolates perfectly. It goes all the way from a near vacuum state on the low end to these heavy, massive configurations as the amplitude increases. Notice how the mass curve hits a peak and then actually starts to dip? That turning point is absolutely crucial. It's the critical threshold. Any configurations beyond that peak become unstable and eventually just collapse right into a chaotic black hole. But it's within that stable, horizonless pocket right before the collapse where all the magic happens. Okay, part 4, 3 pieces of evidence. Time to solve the mystery. We have our suspect, so let's look at the actual proof. I want to explicitly signpost these 3 specific pieces of evidence so we don't get lost in the dense holographic math here.
To prove the boson star is hiding a quantum scar, researchers tested three things. 1, the spectral statistics of its normal modes. 2, its holographic entanglement entropy. And 3, its dynamical Krylov complexity revivals. Let's dive into that first piece of evidence. For clue number 1, researchers probed the star using random matrix theory, and what they found was just a stunning coexistence. At low frequencies, the boson star displays the standard random matrix signatures of chaos, so it definitely still feels the underlying chaotic nature of the holographic universe. But check out the higher frequencies. The spectrum totally decouples into these distinct, equally spaced delta-like peaks. This is huge because it proves that an approximately integrable subsector is hiding right inside this chaotic spectrum. It is the exact mathematical hallmark of a quantum many-body scar. Which brings us to clue number 2, and this brilliantly illustrates the entanglement side of things. In chaotic systems, entanglement entropy is incredibly high. It usually follows a thermal volume law. But when researchers measured the vacuum-subtracted entanglement entropy of the boson star, the results were striking. If you compare it to a chaotic Schwarzschild black hole at the exact same energy density, the boson star's entanglement sits far, far below the black holes. We're talking anomalously low entanglement. And that provides incredibly strong, independent evidence that we are dealing with scarred, non-thermal behavior here. So we have the spectral math and we have the entanglement data. But to really close this case, we have to look at the dynamics. Like, what actually happens if we physically drop a massive proparticle into this system? To measure this, scientists use a tool called Krylov complexity, which basically tracks how a state spreads out over time. And here is our third and final clue. If you drop a particle into a normal black hole, it just falls into the one-way horizon, and its Krylov complexity grows monotonically forever. It just gets endlessly scrambled. But remember, the boson star has no horizon. So instead, as the researchers beautifully mapped out, the particle falls in, reaches the center of the star, and then actually passes through to the opposite boundary, where it reflects. It literally gets trapped, bouncing back and forth. This creates these pronounced periodic revivals, like echoes bouncing around in the system. And this robust, non-ergodic revival is the ultimate dynamical signature of a scar. Basically, the smoothie is unmixing itself. Finally, Part 5, Bridging Chaos and Gravity. Case closed. We've examined the clues, so let's pull all of these incredible findings together. The crucial takeaway here is that these three diagnostics unify perfectly. We have chaotic spectra living right alongside orderly, integrable subsectors. We have measurably subthermal entanglement when you compare it to black holes. And, of course, we have those beautiful, robust, bouncing dynamical revivals. Together, this definitively proves that horizonless gravitational condensates, like our prime suspect, the boson star, really do realize quantum scars. I actually want to read you a quote directly from the source material because it perfectly encapsulates why this matters to you and me. The authors state, and I quote, "Our results suggest that non-ergodic scarred structures can emerge naturally in gravitational dynamics, establishing a bridge between quantum chaos, holography, and horizonless spacetimes. This is a massive deal, guys. It successfully takes the microscopic quantum mechanics of something like a tiny atom array and scales it all the way up to massive, complex gravitational dynamics out in the cosmos." Which leaves us with this final, truly staggering thought. If an effect that was first noticed in tiny, constrained, microscopic models can also define the dynamics of self-gravitating stars, do quantum scars actually constitute a universal organizing principle of the cosmos? Does this secret escape hatch from the universe's ultimate blender extend all the way down to the very fabric of quantum gravity itself? It's the kind of question that completely changes how we view the life cycle of information in our universe. And I really hope it leaves you as hungry to learn more as it does me. Thank you so much for joining me on this explainer.